Transpose graph. Transpose graph problem in which we are given a directed graph with a set of vertices in the form of an adjacency list. The task is to find another directed graph G on the same set of vertices such that all the edges are reversed. As mentioned in the problem statement, we are given a directed graph G that has a set of vertices. Our task is to find another directed graph G dash that has the same set of vertices but with all the edges reversed. Basically, the transpose of the directed graph is another directed graph which has the same set of vertices as original graph but has all the edges reversed as compared to original graph. Suppose there is an edge UV that is from U to V in graph G, then in the transpose graph G dash there will be an edge V comma U that is from V to U. Transpose of a directed graph G is another directed graph on the same set of vertices with all of the edges reversed compared to the orientation of corresponding edges in G. That is, if G contains an edge UV, then the converse transpose reverse of G contains an edge VU and vice versa. Given a graph represented as adjacency list, we need to find another graph which is the transpose of the given graph. We transpose the adjacency list, and as we find a vertex V in the adjacency list of vertex U which indicates an edge from U to V in main graph, we just add an edge from U to V in the transpose graph, that is, add U in the adjacency list of vertex V of the graph. Thus, traversing list of all vertices of main graph, we can get the transpose graph. Thus, the total time complexity of the algorithm is O of B plus E, where B is number of vertices of graph and E is the number of vertices of graph. Note, it is simple to get the transpose of graph which is stored in adjacency matrix format. You just need to get the transpose of that matrix. A transpose graph is directed graph in which it contains the same set of vertices with all the edges reversed compared to the orientation of corresponding edges. In other words, consider a graph which contains edge UV, then transpose of G will be an edge VU. As our focus is mainly representation of transpose graph, it can be achieved by the following two graph representation: matrix adjacency, list adjacency. Matrix adjacency, a total dimensional matrix, row column, where row represents the source vertex and column represents the destination vertex, and the cost of one edge can be stored between each pair of vertex. In other words, consider a directed graph G which G equal to V comma E and its transpose will be G dash equal to V comma E dash is the same as graph G, instead with arrows reversed. For directed graph, G not equal to G dash, but for the undirected graph, G is double equal to G dash. Reason behind there is no arrowheads for edges. Below is the typical two-dimensional matrix approach to represent the transpose of the graph. List adjacency. A graph can be represented in list adjacency in which vertices are stored as objects and every vertex stores a list of adjacent vertex. In this approach, it allows the storage of additional data on the vertex. And additional data can be stored if edges also stored as objects in which each vertex stores its incident edges and each edge stores in incident vertex. Let's consider we have graph G which consists of V total vertex to form a graph G and E total edges to form a graph G. To find the transpose of graph G dash, we need to traverse the adjacency list, and as we find a vertex in the adjacency list of vertex, which is the indication that an edge from U to V in the graph of vertex, we will add an edge from V to U in its transpose graph. Hence, traversing list of all vertices from graph, we can get the transpose graph G dash. A two-dimensional matrix row or column, where row represents the source vertex and column represents the destination vertex. And the cost for one edge can be stored between each pair of the vertices.